we want to show that this limit, this sum 1 plus, we have a double factorial, 2n double factorial, 2n minus 1 double factorial, 2n plus 1 square equals pi over 2 times log 2. So first of all, double factorial just means 2n double factorial just means two n times 2n minus 2 all the way down to 2. So it's the product of all the even numbers starting from 2 up to 2n. Likewise, 2n minus 1 double factorial is equal to 2n minus 1 times 2n minus 3 all the way down to 3. That's the product of all the even odd numbers starting from 3 up to 2n minus 1. So this, first of all, we have to make sure this sum is meaningful, infinite sum. How do we know if this infinite sum is actually convergent? Well, first of all, just so you know that this, we use ratio test, is going to fail in this case, because I'm just going to skip over the calculations, because this series converges very slower than a geometric series. But not using ratio test, we can somehow use comparison test, because 2n minus 1 factorial over 2n factorial. This is already, because you see the 2n is bigger than 2n minus 1. Therefore, 2n minus 1 over 2n is already smaller than 1, bigger than 0. And likewise, next is 2n minus 3, already smaller than 2n minus 2, so on and so forth. So every member of the product is smaller than 1, bigger than 0. So all in all, this is smaller than 1, bigger than 0. So when you multiply by 1 over 2n plus 1 square, definitely going to be smaller than 1 over 2n plus 1 square. So for this guy, we only have to concentrate on 1 over n square. Everything else can be just ignored. So if we consider the series that's made up of this general term, the series definitely converges. This is obvious. So yes, this is meaningful. So how do we know that they actually add up to half pi times log 2? Right? So first of all, we introduce this generalized binomial expansion. So as we all know, that the binomial expansion, we have the constant, combinatoric constant, n choose k. That is equal to the n times n minus 1 all the way down to n minus k plus 1. At the bottom we have k factorial. That's the meaning combination, constant. So we use general. So in general, we have negative half, then we have n. So this time is going to be likewise. So we start from negative half, then we reduce by 1. Then we again reduce by 1 again. So reduce by 2 all the way until here we minus k plus 1. There we minus n plus 1. So n factorial. So this time, so first of all, we notice that we negative half times negative 3 over 2 times negative 5 over 2 all the way. Negative, what is this? First of all, we have common denominator 2, so negative 1 minus 2n plus 2, so minus 2n plus 1. Take out the minus. We have 2n minus 1 over 2. All right? So, yes. So the pattern here is that first of all, we have 2 times 2 times 2 times 2. How many 2's? I think it's n 2's. Right? And negative, negative, negative. N negatives. We have 1 times 3 times 5. That's 2n minus 1 double factorial. Remember the meaning of double factorial. So the reason I know there's n many of them is because if we stop at 3, 3 is equal to 2 times 2 minus 1. So 2 members. If it's n, then it's n members. So exactly. So let me just write it a little bit nicer. So 2n minus 1 factorial. We 2 to the n times n factorial. But notice the bottom is actually what? The bottom is actually, n factorial is n times n minus 1 times n minus 2 all the way down to 2 times 1. And we also distribute each 2 to each one of them. So 2n times 2 times n minus 1. Right? That is times 2n minus 2, right? Also distribute 2 to this one, so 2n minus 4 down to 4 times 2. So that's exactly the product of all the even numbers from 2 all the way up to 2n. That's the 2n factorial, right? So 2n factorial minus 1 is the n, 2n minus 1. Double factorial. Okay, next let's have a look at the generalized binomial expansion. I want to have a look at the 1 plus y to the power of negative half. And so this is so we have to restrict y in between in this open interval, negative 1 to 1. So this is actually the expansion of polynomial expansion or Taylor expansion in infinite series. So this actually expands to 1 plus sigma n from 1 to infinity. The binomial constant, this constant, okay, times y to the power of n. Okay, that is 1 plus from 1 to infinity. 2n double factor negative 1. 2n minus 1 y to the n. Okay. So now I'd like to have a look at the y equal to negative x squared. Right? So that's going to give me 1 minus x squared to the power of negative half. That is equal to, just replace y with, so 1 plus n from 1, 2n double factorial, negative 1, 2n minus 1, double factorial, negative x to the power 2, negative x squared power n. Now, negative 1 to the power n, here I have negative 1 to the power n, so they just cancel out. It immediately become positive, right? So this actually x to the power of 2 to the n, so x to the power of 2n immediately. So this time, what's the relation between this and that? Already looking very similar, except I have 2n plus 1 to the power of 2. Okay, so in that case, I can I can construct a power series. Okay, let's call Sx is equal to, I'm going to plus 1 later. I'm going to first n equal 1 to infinity. 2n double factor 2n minus 1 double factor x to the power of 2n plus 1. I'll explain why it is that. So 2n plus 1 to the power of 2. Okay, so the reason I want to construct x to the power of 2n plus 1, so this is the infinite power series, is because when I differentiate this, I immediately can cancel out 2n plus 1. Okay? So in fact, we can differentiate inside term by term. They're perfectly legal. Right? Long story short, it's because of the infinite series conditions. Right? For this one, every one of them has continuous derivatives. And the series of the derivative is uniformly convergent inside the, not inside the open interval, but inside any closed interval inside this open interval. It is uniformly convergent in here. Therefore, it's also convergent at least at one point. 0 is convergent. So we can differentiate some term by term. So therefore, x is prime. So 2n double factor 2n minus 1 double factor. So different 2n plus 1, 2n plus 1. I only have 2n plus 1. X to 2n. So up to this step, I want to cancel 2n plus 1, so therefore I can have something like this. I can't, if I differentiate 2n, cannot cancel with 2n plus 1. So what do? I multiply by x on both sides. X to the power plus 1, right? So this time I can differentiate. Again, for the same reason, differentiate term by term. Right, and equal 2n double factor, 2n minus 1 double factor, 2n plus 1, 2n plus cancel out. X to the 2n this time. This time it is indeed exactly this, right? Except I plus 1 on this side, right? So in that case, this is equal to this bit minus 1. S prime, x prime is equal to so this is equal to this, equal to this, equal to this minus 1. Negative minus 1. Okay, so far I have 4 equations, and let's not forget their range, domain where they're meaningful. So long story short, the radius of convergence is 1. So this is meaningful when x is within negative 1, 1, open interval. But the problem is that when x is equal to 1, it is, like I said, this is meaningful, convergent, using a comparison test. So let's use right-hand side closed. It's the same reason, right? This one, we can use as Wallis formula to determine its order of infinitesimal. and then use a lim sup to calculate its radius of convergence. Still 1. So still -1 to 1. Right? But when you plug x equal 1 into this, so this again we use some complex calculus. So still meaningful when x is still convergent. Long story short. And so for this one, don't worry about this one. This one is actually x is equal to 1. It's going to be, I believe it's going to be divergent because the order of infinitesimal is n to the power of half. So don't worry about this one. So this, right, focus on this. The derivative of this is equal to that. So which means if we treat x as a constant, we can calculate definite integral. So especially when I want to calculate, because if you imagine, so replace x with t, so a function of t, derivative is equal to 1 times minus t squared, so another function in terms of t, right? So which means this is one of its antiderivatives. So to calculate its definite integral, all we have to do is to figure out the lower bound, upper bound, treating x as a constant, plug in the integrand, here's the integrand, right? Treat x as t. So 1 over square root of 1 minus t squared minus 1 dt. Like I said, treat x as a constant. And now here. So t times s prime t. Okay. Prime equal to 1 minus t squared negative half minus 1. Right? Function of t. Right? Treating. Let me just write one more step. xt. So t right? Antiderivative is equal to so maybe differ by a constant, right? That's the reason. So indefinite integral 1 minus t squared negative half so 1 dt. So this is some antiderivative. This is some antiderivative, maybe differ by some constant. Right? So because you differentiate this, gives you that, the same thing. So treat x as a constant. Right? Definite integral is just replace t with x. Replace t with 0. Right? Exactly how we do definite integral, right? Find its antiderivative, plug in the upper bound, lower bound. So 0 times, so already 0. Right? So this. So this looks fine. This is meaningful when let's still use open interval. Okay, we can actually quickly just calculate the antiderivative of this, because this should be easy. Right, this is negative 1 is easy. Just negative 1 is just minus t, replace t with x, minus x. The first bit is this, but this is the derivative of arc sine of t. Right? Arc sine of t. T equals x, so t equals 0. Gone, nothing. So arc sine x minus x. And in this range, so this is still in this open interval, okay? T is with also with open interval. And so therefore, divide x over s prime is equal to arc sine x over x minus 1. Right? X is open interval. Okay, so first of all, let's remember Sx. So this bit so meaningful in this. So S prime of x, easy, just so easy for us to find out its antiderivative Sx. Right? Perhaps again S t arc sine t minus 1 t is negative 1 to 1. All right, so again, to find out, treat x as a constant. Right? The way we do definite integral is just easily just use s of x minus s of 0. Right? Lower bound 0, upper bound x as a constant. Right? Integrand is easily this bit. Right? Arc sine t minus dt. Of course, x negative 1, 1. Okay, this looks fine. S of 0 is 0. So we immediately Sx. So to find out this, we just let x equal to 1. But how do we know it's meaningful when x is equal to 1 as well? Right? Again, we use Abel's second theorem, right, which says as long as it's this sum function is convergent on the right-hand side of this convergent radius, which it is, so really, right? So the sum function is immediately continuous at 1 from the left-hand side. Left-hand side continuous. So according to the definition of continuous, so S of 1 is equal to the limit x tend to from the left-hand side towards 1. S of x, which is equal to the limit of x tending towards 1 from the left-hand side of this function. So this is a changing upper bound function. Right? Integrate with respect to t, but in the end it's going to depend on x. So 0 to x t arc sine t minus 1 dt. Now, how do we know that this limit exists? Long story short, right? As long as it is Riemann integrable, the changing upper bound is always continuous, right, with the given interval. So continuous, so we know limit actually exists equal to the functional value at this point. So 0 to 1 t arc sine t minus 1 dt. Okay. So minus 1, this bit integral is easy. Just minus 1. This part. Okay, this part. Okay, this part we're going to let... we're gonna arc sine t. U 1 over t is dv. So du is arc sine is 1 over square root of 1 t squared dt. V is log t, so dt. So this integral is uv arc sine t log t 0 to 1 minus 0 to 1 v du log t square root dt. And the second bit is integral of -1. Don't forget that. -1, right? So replace 1 into t. Right? Arc sine 1, don't matter. Log 1, 0. 0 goes into t. Log 0, negative infinity. Arc sine 0, 0. So 0 times negative infinity, it's indeterminate. But long story short, we can use L'Hopital's rule or infinitesimal substitution. Just quickly calculate, still tending towards 0. So this doesn't matter. Just gonna skip all the calculations. So the only thing that this bit is not obvious. So this bit we let t equal sine theta. Right? So dt cosine theta d theta. Right? So this bit negative 0 to, because t is equal to 0, theta equal to 0. T is equal to 1, theta is equal to half pi. Right? Log t, log sine theta. Right? 1 minus t squared, 1 minus sine squared, cosine squared, cosine squared, square root, cosine. dt is cosine, right? Cosine is, so cosine gone. So d theta. Right? So only need to work out this bit. Right? Later we minus 1. And this would be the result of S of 1. S of 1 is x equal to 1 is this bit. Later we plus 1. So plus 1 minus 1, so they can just cancel out. So all we need to do, work out is really this bit, right? But this bit I did it in my last video. 15 minutes long video. I work out. This integral is actually half pi times log 2. Exactly this bit. Without the negative sign, it's going to be negative. But with this negative sign, it's going to be positive. Because if you think about sine theta is 0 to half pi. Sine theta is between 0 and 1. So log of 0 between log of 0 to 1, it's going to be negative. Right? So really this